Hi everyone, I am Gautam, physics faculty. Now I am going to discuss about latent heat. What is this latent heat? So before entering into the latent heat, I want to give small information that if you take any substance, we have totally three phases of matter. Three phases of matter. What are the three phases of matter? Yes, you know that three phases of matter means solid and liquid, and also we can take it as liquid and gaseous state, solid, liquid and gas. So the matter has three phases, three states or phases. We can also call states, three types of states. So we can convert the matter from solid to liquid or liquid to solid, and liquid to gas or gas to liquid, or even you can convert solid to gas. So can any example is there for converting from solid to liquid? Yes, ice to water, or we can also write water to ice. We can do like that. And for any example is there from liquid to gas and like that means yes, water to steam and steam to water, water to steam and steam to water. Sir, solid to gas, any example is there directly can we convert the solid state to gas means? Yeah, we can take one example, basic example as camphor. The camphor directly converts solid to gas without a liquid state. Generally, first solid will convert to liquid and liquid to gas, like that the process takes place. But there is a special situation for camphor directly from solid to gas. Okay, so that we understood that there are three states of matter. So generally what we'll do means, suppose ice at 0 degrees centigrade, we can convert to water at 0 degrees centigrade or vice versa. That means ice at 0 degrees can be converted to water at 0 degrees centigrade. Also we can convert water at 100 degrees centigrade to steam at 100 degrees centigrade. Steam at 100 degrees centigrade or vice versa. The problem is we can't convert ice at 0 degrees to water at some 2 degrees or 3 degrees centigrade. We can't convert. During conversion from one state to other, that is from ice to water or water to ice, temperature constant. Temperature is constant. So temperature remains constant during change of state. Either water to 100 or steam to 100, the temperature remains constant. So during change of state, we have to observe that during change of state, temperature remains constant. Temperature remains constant. Temperature remains constant. This is a very important information to be noted. That is, we can't convert as our wish. That means we can't convert directly ice at 0 to water 2 degrees or water at 100 to steam at 120 degrees. We can't convert like that. Okay, fine. So what is this one? Ice at suppose 0 degrees centigrade. You are converting to suppose water at 0 degrees centigrade. It is called as melting. It is called as melting. And suppose you are converting from water at 0 degrees centigrade to ice at 0 degrees centigrade. It is called as freezing. It is called as freezing. Freezing. Suppose you are converting water at 100 degrees centigrade to steam at 100 degrees centigrade, then we call it as vaporization. Vaporization. Or suppose reverse, that is the steam at 100 degrees centigrade to water at 100 degrees centigrade. This is called condensation. Condensation. So in all these cases there is a change of state or phase. Change of state or phase. Everywhere there is conversion is there. But in all the things you observe, the temperature during conversion is same. Temperature during conversion is same. That's a point to be noted. So at same temperature, the change of state takes place. The change of state takes place. Directly, I can't convert ice. You please observe here, ice at 0 degrees. Directly, I can't convert to water at 100 degrees centigrade. So if suppose I want to convert ice at 0 to water at 100 means first ice at 0 to water at 0. Next water at 0 to water at 100 I can convert. There are some steps. Let us see that one now. So my target is suppose I want to convert, suppose initial ice is at 0 degrees centigrade. First I can make water to 0 degrees centigrade. So here what happened means there is change of state at constant temperature. Change of state at constant temperature. At constant temperature. Next if you observe from water at 0 degrees centigrade to water at 100 degrees centigrade, if you observe, so I am rising temperature from water at 0 to water at 100. Here what happened? Same state, that is a water only, and temperature changes. So these are the two phenomena has to be known. The first phenomena is the change of state at constant temperature. This phenomena belongs to latent heat. This phenomena is called latent heat. And the second phenomena, water at 0 to water at 100, same state temperature changes. This phenomena belongs to specific heat. So I think now you are clear with the difference between latent heat and specific heat. Latent heat is nothing but change of state at constant temperature, and specific heat is nothing but same state temperature changing. That is water at 0 to water at 100. Ice at 0 to water at 0 means ice to water, change of state, and a constant temperature 0 degrees. But now water to 0, if you observe, water to 0 to water at 100 degrees, same state, but temperature changes from 0 to 100. So this is the difference between latent heat and specific heat. Latent heat, state changes, constant temperature. Specific heat, same state and temperature changes. So I think the students, now you are clear with these two things about what is latent heat and what is specific heat. So anyhow, already I explained you about specific heat in detail. Now let us see what is latent heat. Already in a previous video I have explained the information related to specific heat. Now today we are going to discuss about latent heat. So what we understood from latent heat means, here what is the phenomena is happening? Change of state at constant temperature. This is called as what we call, it is a latent heat. Fine, we are happy with this one now. Change of state and constant temperature. Now this latent heat, let me denote with L. This concept they says that here the heat energy is directly proportional to, Q is directly proportional to the mass. So more mass is there, we have to provide more heat to change the state. That means mass is more. For small substance, if you give little heat, this small mass of, suppose this mass is 1 kg here, and I provided the same heat energy Q. This is ice block, suppose ice. By taking Q, it is becoming now water. Ice at 0 to water at 0 have given small, suppose for example, let me take some 1 joule. But if mass is big, now I took M is equal to 3 kg. Now this heat energy is not sufficient to melt this ice piece. Now the mass is more, melting ice piece, we required more heat energy. We required here some more heat energy. So heat energy is directly proportional to mass. So to convert from one state to another state, if mass is more, then To convert to other state, we have to provide more heat. So that's the basic idea. So heat has to be provided more to convert the mass of the substance from one state to another state. So that is the proportionality constant. I am taking it as L. L is a proportionality constant, and that proportionality constant only we are calling it as latent heat. So now latent heat is nothing but Q by M. So here units I can write as joule per kg. Q is the heat energy for given mass. How much heat we have to provide for the mass, M mass? Suppose a mass of substance is M. How much heat energy we have to provide for to convert the state? For convert the state is called as latent heat, is the Q by M. So joule per kg I can write, or I can also write calorie per gram. I can write like that also. Fine. So latent heat I denoted with L. So latent heat is Q by M. Latent heat is Q by M. So what is the definition of latent heat? So here you observe here, I can write that latent heat. When can I write latent heat as a Q? If M is equal to 1 unit, if M is 1 unit, then I can write Q is equal to L. The heat provided is nothing but latent heat. So I can write the definition like this now. The heat energy required, that heat energy may be absorbed or released, that heat energy required, how much energy is required to convert from one state to another state, to convert the substance. Let me try to convert the substance or some solid or something, convert some substance from one state to another state, at constant temperature, So the heat energy required to convert substance from one state to another state at constant temperature is called as latent heat. So latent heat is Q by M. Units I told that joule per kg, or I can also write it as calorie per gram. Like that I can write. So I think now you are clear with the definition. The heat energy required to convert the substance from one state to another state at constant temperature. So this is the definition for latent heat. So L is equal to what I wrote here. Can you observe? It's a Q by M. Fine. So now coming back to this latent heat, it is of two types. So now I am classifying this one into two categories, that is one as LF, other one as LV. LF is called latent heat of fusion of ice. Okay, and what is LV? Latent heat of vaporization. Now the question arises, when should we use this LF and when should we use LV and all those things? What is LF and what is LV exactly? So both the things, no doubt, they are conversion from one state to another state. So first coming back to this LF here, latent heat of fusion of ice, it is nothing but ice at 0 degrees centigrade to water at 0 degrees centigrade, or vice versa. Either ice to water or water to ice. That is at a temperature 0 degrees centigrade. It is called as latent heat of fusion of ice. What is its value? Latent heat of fusion of ice value is 80 calorie per gram. So if you want to check it out in SI units, okay, we can convert like 1 calorie is equal to nothing but 1 calorie is equal to how many joules? 4.2 joules, and 1 gram is 10 power minus 3 kg, and I can write it as 80 into 4200 joule per kg. 80 into 4200 joule per kg. Okay, this is about the conversion. It's in a calorie per gram and it is in SI units joule per kg. My interest is not that. What I want to say is simple point I want to say here is, if you take suppose ice at 0 degrees centigrade, I have taken how much mass? 1 gram of ice at 0 degrees centigrade. So now this one to convert to water at 0 degrees centigrade, how much is heat required means 80 calories is heat required. Either water at 0 to conversion of ice at 0 or ice at 0 to conversion of water at 0. Observe carefully, water at 0 to ice at 0, or ice at 0 to water at 0 of 1 gram, 1 gram of ice to water or 1 gram of water to ice. How much heat energy required? 80 calories. How you know, sir, this 80 calories? This is experimentally given value. Experimentally given value is, but they have checked by providing 80 calories of heat for water, and they observed it was melting for water. Suppose ice, for ice they have given 80 calories, then is melting and becoming water. And for 80 calories of energy is removed from water, then it is converting to ice. How much mass? 1 gram. Remember, don't forget this. I am taking 1 gram of ice at 0 degrees centigrade and I am providing 80 calorie of heat to this one, it converts to water. Or from water, if I remove 80 calories, of heat from water, then what will happen? It is becoming ice. But how much water? 1 gram. For 1 gram of conversion only, 1 gram of ice will become 1 gram of water when 80 calories of heat is provided. So that is represented here, LF value as 80 calorie per gram. 80 calorie per gram. That means for 1 gram, 80 calories of heat is required to do this transition between ice 0 to water 0. I hope you are clear now. Now let us observe the next one. Here I want to discuss about latent heat of vaporization. What is this latent heat of vaporization means? Here this is during conversion, latent heat of vaporization. When we use this concept, during conversion of one state to another state, okay, that is latent heat. What conversion here? Water at 0 degrees centigrade, to water at not 0 here, 100 degrees centigrade. Vaporization means water to steam. So water to steam, water at 100 degrees centigrade to steam at 100 degrees centigrade, or vice versa, either water at 100 to steam at 100 or steam at 100 to water at 100. If you are doing that conversion, then we call it as latent heat of vaporization, LV. So what is this LV value, sir? LV value, they mention it as 540 calorie per gram, 540 calorie per gram. If you want to convert into SI units, that is simply 540 into 4200 joule per kg. How you got this conversion? Just now I explained. I think you are clear. So now 540 into 4200 joule per kg is the LV value in SI units and like that. That means here, if you want to convert, if you have just taken water at 100 degrees centigrade and you want to change to steam at 100 degrees centigrade. So by providing heat, this will be done by providing heat. How much heat is required to do this process means 540 calories of heat if you provide for water. Remember, it is 1 gram. 1 gram of water, if you are giving 540 calories, then it will become water at 100 to steam at 100, or otherwise steam at 100. 1 gram of steam at 100 degrees centigrade is there. If you remove 540 calories, if you take out 540 calories, it will become water at 100 degrees centigrade. If you provide heat, Heat absorbed by water and converts to steam. How much heat we require? 540 calories for 1 gram of water. 1 gram of water, 540 calories if you give, it converts to steam. Or steam at 100 degrees centigrade, 1 gram of steam at 100 degrees centigrade, if you provide 540 calories, it converts to water at 100 degrees centigrade. Very simple thing. Water to steam, steam to water, this process can be done. So for that how much? 540. So that's why we have given the value of LV as 540 calorie per gram. 540 calorie for 1 gram if you provide, then water at 100 to steam at 100 or steam at 100 to water at 100, conversion takes place. This is called latent heat of vaporization. Latent heat of vaporization. So what we noticed about what is L. L is nothing but Q by M, latent heat. We classified into two categories. One is LF, other one as LV. LF and other one as LV. LV we have to write as LV. Now what is this information provided for related to LF? Ice at 0 degree centigrade to water at 0 degree centigrade and vice versa. For LV what should you write? Water at 100 degree centigrade to steam at 100 degree centigrade and vice versa. Steam at 100 degree centigrade and vice versa. LF value 80 calorie per gram. LV value 540 calorie per gram. I hope you are understanding this topic better. It's a very simple, just you have to analyze the topic. Here L is equal to Q by M. So L is called as latent heat. And here what is the conversion? 1 calorie per gram. 1 calorie per gram is equal to 4200 joule per kg is a simple conversion between calorie per gram to joule per kg, because 1 calorie is 4.2 joules and 1 gram is 10 power minus 3 kg. I hope now you are clear with this latent heat topic. The problem is ice and water means whenever ice at 0 degree centigrade is there, we can convert to water at 0. Directly we can't convert to other temperature. So temperature will remain constant during change of state. That you have to remember, don't forget. So water at 0, now it can be transferred to water at 100 by providing heat. This is the first concept, is latent heat of what we call it as. We use here latent heat of fusion of ice. Here we use specific heat of water. Then again from water to steam if you are going, then we use here latent heat of vaporization. So here LF, here SW, here LV. Here in this situation the formula is MLF. In this situation formula is MS delta theta. Here in this situation formula is MLF. So actually we have for Q two formulas we have. One is MS delta theta, another is MLF. ML, simply write ML, don't write F and V, simply write ML. It can be either F and V. So this formula is used when temperature changes in same state. Remember, never forget, temperature changes in same state. And what we have to use ML formula, Q equal to ML when change of state at constant temperature, we have to use this one. I hope you are clear about this Q now. When should we use the MS delta theta formula? When should we use the ML? L can be either LF or LV. So this is the information to be known during the conversions. And one more thing, I want to give one graph for heat provided and temperature changes. This is one of the most beautiful graphs I can say. Just observe carefully here. The heat what I am providing, I am taking on x-axis, and temperature what I am providing, that is taken on y-axis. So let me take some point. This is A. So now when we are heat, suppose this is ice at some temperature, that may be some -20 or -30 something, ice at negative temperature. From ice at negative temperature to bring to ice at 0 degrees centigrade. This is 0 degrees centigrade temperature, and this is 100 degrees centigrade temperature, 100 degrees centigrade. Now observe carefully. First what I did, A to this point, let me call it as B. So A to B, from ice at some low temperature than 0, it may be anything. This point can be either -20 degrees, it can be -30, it can be any point. That is, this point can be -20, -30, -40, anything. Ice at less than 0 degrees centigrade. From there to get 0, we have to provide some heat. Without heat, it can't rise from A to B. After that, it rises its temperature, that means rises its temperature to the point B. Now, from B to C, observe carefully here, B to C, you are giving the heat, temperature is not changing. Here that means either what happens, now there is a change of state here, that is it is converting from 0 degrees ice to 0 degrees water, 0 degrees ice to 0 degrees water. So during conversion, first initially it does not change temperature, will remain constant. Temperature is remain constant, how you understood? By drawing one parallel line to the x-axis. Why x-axis you have drawn one parallel line? Here heat energy is taken on x-axis and temperature on y-axis. If you draw a parallel line to x-axis, means what does it indicate? Y term is constant. What is y term? 0 degrees centigrade. Because ice at 0 degrees centigrade converts to water, ice at 0 degrees centigrade. So this is all is ice, from here to here is ice. So from ice it reached to here, and ice to water it is converting here, and it became water. After becoming water, here what happened? Now it rises its temperature. If you provide more heat, it rises its temperature. If you provide further heat, what will happen? It rises its temperature until it reaches 100 degrees centigrade. So it reaches the 100 degrees centigrade temperature. Once it reaches 100 degrees centigrade temperature, then still we are providing heat, because see here we are providing still heat. First from A to B we provided heat here. So rise it from temperature -20 or -30 to 0 degrees. From 0 degrees, when we are providing more heat, it is taking heat but not changing temperature, is changing state and became water. Now after becoming water 0 degrees centigrade, now it is increasing. When we are providing heat, it is increasing temperature and reaches maximum point is 100. Once it reaches the maximum point as 100, now what will happen? Now it will again convert from water at 100 degrees centigrade to steam. So it is converting to steam. So water plus vapor, I can write here water plus vapor. So from water it is converting to steam. So here what happened? Water to steam. It is converting to steam. So in this process, first what happened? Carefully observe. From some temperature lower than 0 degrees ice, rise it to 0 degrees ice. Temperature increases by taking the heat. And again by taking the heat, temperature is not changing and became ice at 0 to water at 0. Again now this water is taking heat, and by that heat it is increasing its temperature from where to where? 0 to 100 degrees centigrade. And again at 100 degrees centigrade, if you provide is further heat, now water is converting to steam. Water is converted to steam and is going like that, and superheated steam. Now at this point we can call it as superheated steam. Like that we can draw the graph between heat on x-axis, temperature on y-axis. So here you can clearly observe in this graph, if you take what is this one, what is the formula first of all for length of BC. See, length of BC is nothing but, what is length of BC? So BC means if you observe, it is related to latent heat concept, is related to latent heat concept, is related to LF. So here this is related to latent heat of vaporization concept. This is related to specific heat of water concept. This is related to specific heat of ice concept here. So this is here what we use the formula means ms ice delta theta, here mlf, again ms delta theta, again mlv, like that we'll use the formula for heat. So now what is length of BC? Length of BC is directly proportional to latent heat of fusion of ice. Length of BC is directly proportional to latent heat of fusion of ice, and length of this point BC, and let me write this point as D and this point as E. So now length of DE is directly proportional to latent heat of vaporization. Length is directly proportional to latent heat of vaporization. So from here we can also identify that actually in the question we know that from the diagram LV is greater than LF, LV is greater than LF, because length of DE is greater than length of BC. Length of DE is greater than length of BC, so LV will be always greater than LF. Latent heat of vaporization is greater than latent heat of fusion, latent heat of fusion of ice. We also know the values, right? LF value is 80 calorie per gram. By just taking 80 calories from here to here, it takes how much calories? 80 calories if 1 gram if you take. From here to here it takes 540 calories if you take 1 gram. So like that LV value is 540 calorie per gram, 540 calorie per gram. So we know that LV is greater than LF. LV is greater than LF. And slope of the graph. Actually what we are taking here we are taking heat energy here, and what is this one? Temperature difference. That means temperature on y-axis and heat energy on x-axis. What do you mean by slope? Slope of the graph is nothing but tan theta. Slope of the graph is nothing but tan theta. So tan theta again is nothing but difference in y-axis by difference in x-axis by y-axis by difference in x-axis. What is then y-axis? Temperature. So small difference in temperature by the difference in heat energy, because this is called as a slope. So here the temperature difference, let me take it as dt, and this is a dq, and this angle is called as tan. Now this is theta, so that what is the slope of any straight line graph is tan theta. Slope of the graph is tan theta. So from here easily you can identify that in this triangle you can identify that tan theta is dt by dq, dt by dq. So we know that dq is equal to ms dt. We know that dq equal to ms dt. From here what is dt by dq? Dt by dq is nothing but here dt by dq we are writing, right? Dt by dq means what we can write? 1 by ms, 1 by ms. So dt by dq is equal to I can write it as 1 by ms. Why means dq equal to ms dt, and what we required here tan theta, because we are taking temperature on y-axis and heat energy on x-axis. The difference, that means if you take the small part of the graph here difference in temperature is dt and heat energy is dq. So what is the slope? Slope is nothing but tan theta. Tan theta means opposite by adjacent. Opposite is dt, adjacent is dq. So tan theta is dq. Tan theta is nothing but slope. Tan theta is nothing but slope. So dt by dq. So I can also write now from here what I understood is slope is nothing but 1 by mass into specific heat. 1 by mass into specific heat. From here you can understand that slope of AB graph, in the previous graph if you observe, slope of A to B, observe carefully, I am taking from where to where? A to B. Slope of AB graph, slope slope of AB is related to what? Ice. And here what slope of this one? What it belongs to now? Here if you observe this part, slope of CD. Yes, slope of CD if you take, it is nothing but is related to liquid. It is related to liquid. Liquid means water and AB means related to ice. Let me write that points. So slope of AB in that previous graph, slope of AB is directly proportional to 1 by mass into specific heat of solid. Observe AB, AB you observe, AB you observe, A to B, A to B, it is ice, it is solid, A to B is ice, solid, and C to D, it is liquid, water, it is a liquid. So that I can write here, slope of AB is, and again slope of A, what should I write? Slope of CD, slope of CD is inversely proportional to 1 by m into S into liquid. It is nothing but liquid. Very simple. Nothing to get worried about that. You just observe this line slope. This line slope is nothing but 1 by mass into specific heat of ice. Here 1 by mass into specific heat of water. Specific water only I am calling as liquid. Ice only I am calling it as solid. Nothing other than that. You no need to get any confusion in that regard. Just observe carefully here. Simply mass into specific heat into, because we know slope is 1 by ms. AB line related to ice, ms solid, and again slope CD line related to liquid, ms liquid. Like that I can write ms of solid, s of liquid. Like that we can write information from the given graph. Very simple to understand this graph actually, frankly speaking. Here what happened, first the temperature is very low than 0 degree centigrade, rise to maximum to 0 for ice, and after ice at 0 it converts to water at 0. This is a melting, we can call melting. After melting, water at 0 it converted to water at 100, water at 100 it is now converted to steam, steam further temperature rises. So heat is given in x-axis and temperature on y-axis. As going on heat increasing, during some time I notice temperature rise, and during some time even heat is increasing, temperature not rising, is changing the states. A to B heat rises, temperature rises. B to C heat rises but temperature constant and state changes. C to D, here heat is increasing but temperature is also increasing, heat increases, temperature increases. But D to E, heat increases but temperature constant, it's just a state conversion. Again from E onwards, again steam is increasing its temperature by taking heat. So this line A, B, C, D and E, after E you can observe these three lines, A, B line, C, D line, and let me write some point here, it has some F like that, E, F line. If you observe these three lines, A, B line, C, D line, E, F line, here by taking the heat, the temperature has been increasing, temperature has been changing. But BC and DE not like that, BC and DE not like that. There they are changing from one state to another state, that is from ice to water, here water to steam. That is a given information related to this graph. So what happened means, in today's class I started my journey with latent heat. So here what is latent heat, we started from that point and slowly we went step by step and we discussed the remaining points. See here, first three phases of matter, solid, liquid and gas. So three phases of matter will be there. So I one state to another state, during conversion temperature remains constant, and ice to water, melting, water to ice, freezing, water to steam, vaporization, steam to water, condensation, like that we discussed. Then ice to water, water to water, 0 to water at 100. What is happening? First ice to water, that is change of state, constant temperature. Water to water at 0, water to 100, change of temperature at change of temperature in same state. So this concept related to specific heat, this concept related to latent heat. Slowly we entered into latent heat and we wrote heat energy is directly proportional to mass and from there we got the expression as the proportionality constant L, and we got the latent heat formula, and we discussed the definition of latent heat. After that, latent heat classified into latent heat of fusion and vaporization. LF is when ice at 0 to water at 0 and vice versa. LV is from water at 100 to steam at 100 and vice versa. And here I wrote L values, LF values and LV values, and that information related to latent heat. Then after that I have told that when we are going from ice to water, what is happening, and water to steam, what is happening, we discussed. And we discussed about this graph. Finally, heat taken on x-axis, temperature taken on y-axis. Different situations, from taking ice at some low temperature than 0 degrees, and we rise it to 0, and from ice at 0 to water at 0, water 0 to water at 100, water at 100 to steam at 100. Finally, steam is rising its temperature. I hope you are clear with this, all the things what I discussed in this class. Thank you.